Welcome to Math Monday. My name is Miss Barnes, and the segment that follows is for kindergartners through second graders. Friends, this morning our lesson looks a little bit different. Okay? We're not going to be focusing on problem solving. Today we're going to start developing a concept called place value. Okay? Place value is the idea that different digits in a number have different values. We read at the very beginning of our homeroom time together, we read a book called Zero the Hero. And Zero taught us the value of numbers in different positions. So today we're going to start to develop that concept. You will need your 10 frame. This is the one that I created a couple weeks ago with you. And you'll need some counters. Now I'm doing all of our work digitally, so you won't see me working with these tools. But you will need your 10 frame and something that you can use to organize your counters or your toys or your pieces of cereal. You will need a double 10 frame. You'll need 2 of those today. So why don't you take a second now and let's get ready to learn. All right, friends. So our objective is I can compose and decompose numbers from 11 to 19. Remember when we started our journey together that we talked about composing and decomposing. And composing just means that we're going to take 2 parts and put them together. Decomposing is the opposite. Decomposing is taking the whole and breaking it into parts. Today we're going to be doing a lot of composing, but we're going to talk about how to break down a number into its pieces, decomposing. So we are going to jump right in to our first problem. Don't forget to have your 10 frame and your counters, whatever you're using as counters, ready. Okay, so the first number that we are going to talk about today, remember I told you that this isn't problem solving. So we're just going to talk about numbers today, what they look like, and how you can compose and decompose them. And the first number that we're going to talk about is the number 12. 12 is a 2-digit number. That means the value of one digit is going to be different than the value of another digit. So the first thing that we need to do is we need to count 12 counters. Whatever you're using as counters, I need you to count 12 of them now and just set them down on your table or your floor, wherever you're working. After you have counted 12, we need to organize them into the 10 frames. So let's take a second to do that now. And I'm just going to take my pile of counters and I'm going to move them into the 10 frame so that I can tell more about the place value in the numbers. So here's 9 and 10. And then we have some leftovers. And we'll just put the leftovers in a separate 10 frame down here at the bottom. Now let's talk a little bit about what we already know. Here at the top, this 10 frame is completely full. Do you remember what we call that? We call that a 10. A 10 is the same as 110. And 110 is the same as 10 ones. That means that what you see in the top 10 frame can be equal to 10 ones, but is also called a 10 in math. Now we're going to look at the bottom 10 frame, and you'll see in the bottom 10 frame that there are how many counters, how many leftovers are there in the number 12? That's right, you see 2 leftovers down there, and we're going to call those ones. Okay? So that means that 12 is composed of 110. Try again, my tool didn't work. 12 is composed of 110 and 2 ones. So let's look back up to the number and see if we can find any similarities between this answer at the bottom of our screen and the number at the top of the screen. Do you notice any similarities between those? Well, I notice that there's a 1 here, and that we also said that the 12 is composed of 1 10. I also notice that 2 here is the same as the 2 1s we calculated with our 10 frames. So remember when we started, I told you that 2-digit numbers are composed of 10s and 1s. The number on the left on your screen, it's the yellow number, the highlighted yellow number. That number represents the amount of 10s in a 2-digit number. The pink number, the digit on the right, represents the number of 1s in the same number. So 12 we know is composed of 1 10 and 2 1s. Great job. I know that was hard work. Let's move on to the next one. The next number we are going to be working with is just a bit larger than 12, and it's the number 14. Okay? So we're going to look at 14 counters. So if you are counting with me, I need you to count 14 counters out and organize them into your 10 frames, just like I'm doing here. I'm going to stop here for a second because I want to see if you remember. Do you remember how many is in a row of the 10 frame? It's not 10. How many is one full row of the 10 frame? That's right, that's 5. Great job. So we're going to keep counting on 5 until we get to a full 10 frame, which is 10. And now we're going to put the leftovers in the bottom 10 frame. Hopefully you're working along with me. And now they're all organized. So let's do some drawing here and let's talk about what we have. Here's another case of a full 10 frame. Okay. What do we call that? We call that a 10. A 10 is the same as 1 10, and 1 10 is the same as 10 1s. Then we have to count what's left over in the second 10 frame. And that leftover down here is how many? Count them, go ahead. There's 4 1s, great job. So that means that 14 is composed of 1 10 and 4 1s. Now, we reviewed a couple things here that I want to make sure you heard. We also know that when we have one row of a 10 frame full, that is 5 1s. So then we double that to get a full 10 frame. 5 doubled is 10. And then we counted the leftovers, and we said that was 4 1s. So remember, when we look at a number, a 2-digit number specifically, when we look at a 2-digit number, the first number you see tells how many 10s are in the number, and the second number tells how many 1s are in that number. Now there's one more problem to do together, one more number to sort out, and that number is even bigger than 14. And the last number we are going to work with is 17. So 17, if I write it up here, looks like this. And now here with my counters, I have to count 17 of them. As you're counting, don't forget to organize. The more you organize, the easier it is to count the counters later. It's also much easier to decide how many 10s and 1s are in the number because it's easier to see. So there's a full 10 frame, 11, 12, 13, 14, 15, 16, and last but not least, 17. Now, you may be able to go ahead and fill out the sentence that's on the bottom, and that's great if you can. But if you can't, we're going to go through the process one more time just to make sure you got the right answer. So here on the top, remember that that is a full 10 frame, and we know that a full 10 frame is equal to 10 ones. But we also know that 10 ones is called a 10. And we also know that a 10 is the same thing as 1 10. So here on the top, we have 1 10. Then we have to count the leftovers in the bottom 10 frame. And the leftovers, keep changing it. The leftovers here in the bottom 10 frame, how many are there? Maybe you don't need to count them. So remember that the top row has 5. And then remember that the bottom 2 counts on. So the top row is 5, the bottom row is 6, and then 7. So how many ones do we have? Well, we have 7 ones. So that means that 17 is composed of 1 10 and 7 ones. Going back to the number, I bet you could have told me that before we did any work, right? So looking at the number on the top, 1 10 is the same as the first number, and 7 ones is the same as the second number. So always remember that. A 2-digit number is composed of 10s and 1s. The 10s digit is the first digit you see. It's always the one on the left. The 1s digit is always the digit on the right. If you can remember that, you're going to have a much easier time adding. Thanks for joining me in class this week. I had a great time, and I can't wait to see you next week. Bye.
Kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
Good afternoon, boys and girls. This is Ms. Shields from Faxon Elementary. Today, I am here to help you with adding and subtracting fractions with unlike denominators. Let's go ahead and get started. You will see on my screen that I have 5 simple steps that you can use in order to help you with these types of problems. Feel free to write them down so that you can go back and reference them in your notes later. Step number 1, we are going to read the problem. Step number 2, write out the problem. Step number 3, find the LCD, or least common denominator. Number 4, rewrite and solve the problem. Number 5, simplify if it is needed. So we're going to start back up here at step number 1, and we're going to read the problem. Yesterday, Carson threw away 1 1/3 pound of paper packaging. He also threw away 3/4 of a pound of plastic packaging. Altogether, how many pounds of packaging did Carson throw away yesterday? I have to ask myself, what is this asking me to find? In this case, it is asking me to find out how many pounds of packaging Carson actually threw away. This word altogether means we have to combine things together. We're putting them all together. And what are we putting together? We are going to put together the 1 1/3 pounds of paper that he threw away and combine that with the 3/4 of a pound of plastic he threw away. So we are ready for step number 2. We're going to write out that problem. So I'm going to write our problem. We're going to have 1 1/3 And since we are going to combine it, that means we're going to add. So we're going to add 3/4. I'm giving myself plenty of room so that it is easier for me to work out our problem and things aren't all bunched up together. Okay. The next thing we're going to do is find the LCD, or the least common denominator. So in that case, we're going to keep a list over here of our least common denominators. And the denominators that we are working with is a 3 in 1 1/3 and a 4 in 3/4. So we are going to find the least common denominator of these two numbers. And we do that by skip counting. So I'm going to count by threes. 3, 6, 9, 12, 15, 18, 21. And then down here, I am going to count by fours. 4, 8, 12, 16, 20, 24. So now we need to look at this and decide which one is the smallest one that they have in common. So I always like to start with the bigger of the two numbers and use those multiples first. So we have 4. Do you see a 4 up here? I do not see a 4. Then we have an 8. Do you see an 8? We have a 12. Do you see a 12? Of course, and so 12 is going to be our least common denominator. We are now going to use that 12 and go to step number 4 and rewrite our problem. So we have to rewrite our problem using 12 as a denominator. So my problem is now going to read 1 and something over 12, and this one will read something over 12. So now we need to decide, what is that something that goes there? So I look and I have to decide 3 times something equals 12. I can go back over here and decide it's 1, 2, 3, 4. 3 times 4 is 12. And if I multiply the bottom denominator by 4, I have to multiply the numerator by 4. 1 times 4 is 4. Now we follow that same step over here and decide 4 times something equals 12. 4 times what equals 12? 1, 2, 3. 4 times 3 equals 12. And whatever we do to the bottom, we must do to the top. Very good. 3 times 3 is 9. We have now rewritten 1 1/3 as 1 4/12 and 3/4 as 9/12. We can now solve that problem by adding them together. First thing I need to decide is I have a whole number here of 1. I do not have a whole number, so this is the same thing as 1 plus 0, and 1 plus 0 is 1. And then we have 4 plus 9. 9 plus 4. That equals 13. And my denominator is going to stay the same since we found a common denominator, and my denominator will still be 12. Step number 5 is to simplify if we need to. We know that we need to simplify this problem because it is an improper fraction. Our numerator is larger than our denominator. So I have to think about how many pieces made up my whole. And we said 12 pieces made up a whole. If I had 12 out of 12 of them, then I had one whole. If I have one hole here and I have one hole here, I am going to be left with 2 holes. But how many do I have left here? Well, 13 minus 12 is 1. So I have 2 and 1/12. I'm going to show you what this looks like when we are using fractions, fraction strips. So on here I have fraction strips that are divided into 12 pieces. I'm going to go ahead and I'm going to color in that 1 4/12. 1 hole, so I'm going to color in the whole thing. And then I'm going to shade in 4 out of 12. 1, 2, 3, 4. We added to that 9/12. So 9 out of 12. So we're going to count 9 more. 1, 2, 3, 4, 5, 6, 7, 8, 9. You now see that what I have shaded is 2 holes and 1 out of 12, or 1/12. So I have 2 and 1/12. Which is what we got here as our answer. So we did a very nice job following those steps. We're going to see if we can follow those steps again, and this time we're going to try to work through a subtraction problem following our steps. So step number 1, we're going to read the problem. Mike has 1 5/12 books left to read for a school project. Mike read 1 1/9 books on Sunday. How many more books does Mike have to read? Again, we ask ourselves, what are we trying to find? In this case, we're trying to find how many more books does he have to read? How many more means that he read some, but he still has some more that he needs to read. So he has to read 1 5/12. He has already read 1 1/9. We need to use those 2 numbers to decide how many more does he need to read. So we're going to write out our problem. We're going to start with 1. And 5/12. That's how much they said he has to read for his project. But he has already read, so we're going to take away what he already read, and he already read 1 and 1/9. So our problem now is going to be 1 5/12 minus 1 1/9. We're going to find that LCD, or that least common denominator. What are the denominators that we are going to use? I see we have a 12 and we have a 9. So we are going to skip count by 12s. 12 times 1 is 12. 12 times 2 is 24. 12 times 3 is 36. 12 times 4 is 48. 12 times 5 is 60. 9 times 1 is 9. 9 times 2 is 18. 9 times 3 is 27. 9 times 4 is 36. 9 times 5 is 45. So now we have a list of our multiples. Now we need to find which one do they have in common. What is the smallest one they have in common? Since 12 is our bigger number, we're going to start with the 12. Do we have a 12 in this row? No. Do we have a 24? No. Do we have a 36? Yes, we do have a 36. So 36 is going to be our LCD, or least common denominator. So we need to rewrite our fractions using 36 as our denominator. I didn't leave myself enough space on this one, so please make sure you're leaving yourself some room when you are solving these problems. Okay. So 12 times what equals 36? We go right back over here. 1, 2, 3. 12 times 3. Whatever we do to the bottom, we must do to the top. So 5 times 3 is 15. 9 times what is 36? 1, 2, 3, 4. 9 times 4. What I do to the bottom, I have to do to the top. 1 times 4 is 4. Now we are ready to solve that problem. We're going to subtract our whole numbers first. 1 minus 1 is 0. 15 minus 4. 15 minus 4 is 11. My denominator stays the same, so I have 11 36ths of a book left to read. If we go through and we look at that using our fraction strips, we had one whole, that's the whole book that he read. And he had 15 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 36. Now he had already read one whole book. He had read this whole book. So he read all of this, and then he read 4 out of 36, and you'll see what he has left is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of that 36. So he had 11 36 remaining. 11 36. That is all I have for you guys today. Please come back and watch some more videos, and if you have any questions, let us know. Have a great day.
The desire to create lives within each of us. From Grammy-winning producers and musicians, to NBA stars, to Navy admirals and Medal of Honor recipients, to internationally renowned artists and beloved local muralists, Paseo graduates have been creating their own success, their own history, their own legacy since 1926. Now it's your time. Create your future at Paseo Academy of Fine and Performing Arts. Learn more at enrollkc.org/Paseo.
Hello, my name is Mary Jo Bender, and this is Math for Middle School. Today we're going to go over how to compute constant proportionality between quantities using the values in graphs. What you'll need today is paper and pencil. Okay, take a quick second, let's get ready to learn. Last week we talked about how tables are proportional. And when we talk about proportionality, we want to look at the two quantities and they need to share a common ratio. Now, that common ratio is called a constant of proportionality. And you can find that the constant of proportionality by using the equation k equals y divided by x. In the table, as you can see, this is a proportional table and it shares some common characteristics. The first is the change in x is going to be constant. Now, the left-hand side of your table is going to be your x value. And if you notice, each of the lines or each of the quantities in the x tables differs by 3. So we would say that this has a constant change of 3. The second characteristic is the constant change in y. And in this table, as you can see, the constant change in y is 5. Now, when we look at that constant proportionality needs to carry out throughout the table. It doesn't have to be the same left to right side or x to y, but all of the x need to have that constant change, all of those y's. If we also look, we can say, okay, I can divide each of those y divided by x down to a common ratio, which is 5 to 3 or 5/3. Now, let's take a look at this, how it looks in a graph. So, when we talk about proportional relationships in graphs, we're really looking for two things. The first is that it starts at the origin. Origin has an ordered pair, and that ordered pair is 0, 0. As you see, the table on the left does start at the point 0, 0. The graph on the right does not. Here's 0, 0 on the one on the right. You'll notice it starts at the ordered pair 0, 10. Automatically, if a graph does not start at the origin, it's going to be non-proportional. The second thing we're looking for is a straight line. Does it have its straight line going through the rest of the graph? The one on the right does, the one on the left does as well, but because the one on the left is the only one that starts at the origin, we're going to say this graph is proportional. For a graph to be proportional, it must have both characteristics. It can't just have one or the other. So let's look at some examples. Our first example is we have a situation, Victor is making a backsplash in his kitchen. And the table suggests that we have rows 0, 1, 2, 3, and 4. The y value, or the number of tiles, represents how many tiles are total in those rows. So if we notice 0, 0, we can make an ordered pair by taking the left column and the right column, putting together. This represents the x, this represents the y. And when you put your ordered pair together, make sure you put your x on the left, your y on the right. So if we look at our graph, we're going to start at 0 and we're going to go up 0. So yes, in fact, it does start at our origin. That's our first requirement. The next one is we're going to go ahead and plot our points. So we're going to go 1, 7, and we're going to put that dot there. Then we're going to go 2, 14. Make sure when you're plotting these points, you always do the x value first. 3, and then we're going to go up 21 is going to go right there. And then the last one, 4, 28, it's going to go right there. Now we're going to draw a line starting at 0. And my line is straight. So because I have our two characteristics beginning at the origin and our line is straight, we're going to say that this graph and this relationship for Victor and the backsplash is in a proportional relationship. Let's take a look at another one. So this time we have the perimeter of our square based on the length of the sides. Now we're going to go ahead I'm going to go ahead and plot the points for you as I read you the table. Remember, our left side is our X, our right side is our Y. When we do our ordered pairs, we're going to put X, comma, Y. Make sure they're in that order. If they're not, it's not going to work out too well for you. So we're going to start at 0. We're going to go up 0 for our first ordered pair. Okay, it's looking pretty good for us because we do have our origin now. And then we're going to go over 1 and up 4. Now you'll notice that my over 1 is actually over 2 because this middle line represents 1/2. So make sure you're looking at those scales on your axes because sometimes they'll do what I call skip counting and you might accidentally put it on the wrong spot. Okay? So our third ordered pair is going to be 2, 8. Then we have 3, 12. And then we have 4, 16. As you can tell already that our line is going to be in a straight line because I've already drawn an imaginary line and I can see that straightness coming through. Always go ahead and draw your line and make sure it's straight. Our two characteristics starting at 0, 0 in a straight line, we're good to go, so this graph is proportional. So let's take a look at Angie. Angie's going to get paid for babysitting. Now you'll notice the first thing, here's our X, here's our Y, that's always the first thing I look for. Our first ordered pair is going to be 0, 14. So when I go over 0, I'm going to start at 0 and go up 14, notice how it's not going to start at the origin. So right now, without even drawing any more lines, I know that this graph is non-proportional. Now, one thing that you need to remember when a graph is non-proportional, that point 0, 14 means that Angie's going to get $14 for just showing up. She's not going to work any time at all and earn $14. Let's go ahead and graph so we can see if this forms a straight line or not. It may not have either of our characteristics. So we're going to go over 2 this time. Remember, it's skip counting. That's 1/2. So we're going to go over 1, up 21. We're going to go over 2, up 28. Over 3, up 35. Over 4, up 42. Now you'll notice you can draw a straight line using this. So it does have our straight line characteristic, but you'll notice it doesn't start at the origin. So because of that, we automatically have to kick it out at non-proportional. Now let's take a look at some graphs. Remember, our two characteristics for proportional graphs is one, that it begins at the origin. The second, it has a straight line through the graph, including the origin. So if you notice, this particular graph does start at our origin. Right there it is. It does have a straight line going through the origin, so we're going to say this graph does meet our characteristics for proportionality. So we're going to call it a proportional graph. Let's take a look at another one. Remember, our two characteristics goes through the origin in a straight line. Well, right here is our origin. Notice that our graph is all the way down. It doesn't go through our origin. It actually crosses at 0, -3. So our origin ordered pair 0, 0 isn't in play here. So automatically, even though it does contain a straight line, we have to say it's non-proportional. Let's take a look at another graph. This graph I kind of like. It's kind of one of those whimsical graphs. And notice, remember our two characteristics? Goes through the origin, straight line. Here is our origin. The line goes through the origin, but really is it a straight line? No, it's not. It's really one of those wacky curvy lines. So because it only has one of the characteristics, this particular graph is non-proportional. That concludes our lesson for today. Let's take a quick review. Remember, I have two graphs here. The characteristics of proportionality between quantities on a graph is it must begin at the origin. And remember, the origin has an ordered pair of 0, 0. We look for those in tables as well. And we also have a straight line throughout the entire graph. You'll notice our first graph does start at 0, 0, and it tells us that we don't have any cost for the number of hours, whatever our labor happens to be. And if you come over in savings account, notice our first ordered pair is right here, and that coordinate is 0, 20. So our account is actually starting with $20. So it doesn't start at our origin, so it's not proportional. Even though it does show a constant rate of increase throughout our savings account, it's non-proportional. So this is our only graph, the one on the right, that would be considered proportional. It has our ordered pair, 0, 0, and it has a straight line. Remember to work on your proportionalities during the week so you can continue to improve. It's been my pleasure working with you today in class. My name is Mary Jo Fender, and I'll see you next week.
Southeast because of the culture, the band program, and restorative justice.
I love Southeast because of the academics, sports, and students.
I love Southeast because of the people, the energy, and the advanced classes.
It's not alike. I love Southeast because the students here at Southeast are full of potential and they believe in achieving anything.
We are Southeast. Southeast. We stand shoulder to shoulder.
Join the Southeast family. Enroll today.
Hello, my name is Marcelina Lirius and welcome to Math Monday. In this video, I will show you how to represent functions in multiple ways. Please get your pen and your notebook and be ready to take down notes. At the end of this session, you should be able to represent functions in different ways, such as using a mapping diagram, input-output table, a graph, a set of ordered pairs, or an equation. So what are the different ways of representing functions? And what information do the function representations give us? Okay, let's start with some vocabulary. So when we say a relation, it's a set of paired numbers which we call ordered pairs or objects, x and y, where x is called the input value and y the output value. We have a special relation which is called a function. And when this pairing is, when x is paired with exactly one value for y, we call this relation a function. So each input x is paired with exactly one output value for y. Let's take the first example. We're asked to express the relation given the set of ordered pairs as a mapping diagram, table, or graph. So if we are given a set of ordered pairs, the first number in the ordered pair represents your x, or the input, and the second number represents y. So in this case, x is -1, y is 0. In the second pair, we have x is 1, the second value is 2. So it will be in the y set or y value. Then the third pair is 2 and 3. So the first number is 2, it's the input value, and the y value is 3. And 4, 6, we now have 4, 6. So this is one representation of a function called a mapping diagram. So we pair each element in x with another element in y. So 1 is paired with 2, 2 is paired with 3, and 4 is paired with 6. The question is this relation a function? Going back to the definition, when we say function, each element in set x is paired with exactly one element in set y. So this is called a function. Okay. Now, if we are to represent this ordered pairs, same ordered pairs in table form, so we now have our x values, so have x -1, 1, 2, and 4. So you now have here x -1, 1, 2, and 4. These are the first values in the ordered pair. So we call this as our input. And looking at the second values, we have 0, 2, 3, and 6. So 0, 2, 3, and 6. We call this as our output values. So this is another way of representing a function using an input-output table. So we have x and y side by side, but you might also want to express this when x and y are, the top-bottom way, when you have your x here, then y. So this is another way of representing the function in table form. So you have -1, 1, 2, and 4. 1, 1, 2, and 4. Then the second values are 0. You have 0, 2, 3, and 6. So this is another way of representing the table using the top and bottom representation. Okay. Another way of representing a function is using a graph. So what we're going to do, given these ordered pairs, again, these ordered pairs x and y, this is an ordered pair wherein the first element is x and the second element is y. So when we plot the point -1, 0, so this is the point, -1, 0. We now have one end, so this is -1, 0. This is the point 1, 2. Another point here is 2, 3, and this point is 4, 6. Okay, so all these representations, graph, input, output table, and the ordered pair are all representations of the same function. I'll stop, process the information, take down notes. Okay. Next, so we can also represent a function using an equation, and from the given equation we can rewrite this in or represent this in table form or as a mapping diagram or a graph. So let's have this example. The equation y equals 2x plus 5 represents the relationship between the total amount y is the total amount, and the number of rides x. So Henry spent at ABC event that charges $5 entrance and 2 per yard. Now let's look at another example. So one way of representing function is using an equation. So in this example, we are given the equation y equals 2x plus 5 that represents the relationship between the total amount y and the amount or the number of rides x. So Henry spent y amount of dollars at ABC event that charges $5 entrance fee and $2 per ride. So the 5 here in the equation represents the entrance fee, and 2 here is the amount you pay for each ride. So x here represents the number of rides. So if we represent this function using a table, let's start with substituting our values for x. So since this is an amount, we cannot represent, or x represents the number of rides, so we start with 0. That means we just entered the event or enter the park. So you are already, even without getting any ride, you already pay for the entrance fee, which is $5. So that means x is 0. So when x is 0, you have not taken any ride, so you substitute 0 here. 2 times 0 plus 5, so which is 0 plus 5 is 5. So you now have the first pair, 0 and 5. So when x is 0, y is 5. Then, if we substitute, if Henry takes 1 ride, we substitute this value for x in the equation. So y equals 2 times x, or 2 times 1 here, plus 5, and simplifying this, 2 times 1 plus 5 gives us 7. So we now have another pair when x is 1, y is 7. And when x is 2, we substitute 2 into the equation. Y equals 2 times 2 plus 5, which is 9. So we now have another pair 2 for x. Y is 9. And say, for example, x or Henry rode 5 rides there, or took 5 rides. So substitute 5 to x. So 2 times 5 is 10 plus 5 equals 15. So if we have 5 and 15. So this is now the table that represents the equation y equals 2x. And this is the mapping diagram that associates all values for x, that means the number of rides and the amount that Henry will pay. So here we have the equation, we have the table, and we have this mapping diagram. All three representing the same function or same relationship. So given the same function here, y equals 2x, we already have the table here. Substitute x and y, get the value for y. So if we plot the points, when x is 0, we got 5. So this is the point. When x is 1, we got 7 earlier. And 2, we get 9. And if we substitute x is 3 here, 2 times 3 plus 5 is 11. So y is equal to 11. So these 4 dots here represent the points or the ordered pair representing the function. Okay. Okay, in the next example, we are asked which of the following represent the same function. So these are different ways of representing function. We have a set of ordered pairs. You have an equation. You have a mapping diagram. You have another equation and a graph. Of these 5, which of these represent the same function? Okay, so if I have the ordered pairs -1 paired with -4, 0 is paired with -1, 3, 8, 6 paired with 17, will this represent this equation y equals 3x minus 1? So which means if we substitute these values when x is -1, it will give us -4. So 3 times -1 is -3, minus 1 is -4. When x is 0, that's 3 times 0 is minus 1 is -1. Okay. When x is 3, 3 times 3 is 9, minus 1 is 8. That's correct. And when x is 6, 3 times 6 is 18, minus 1 is 17. So a and b represent the same function. And if we look at the mapping diagram, you now have 1 is paired with 4 from the ordered pair, 0 is paired with -1, 3 is paired with 8, and 6 is paired with 17. So we know earlier that these 3 now represent the same function. And let's look at the graph first, letter E. So if we have y equals 3x minus 1, so let's check if this graph represents also the same function as B. Knowing that the 3 already represent the same function, let's check if B and E are, representing the same function. So y equals 3x minus 1, so when you have x, okay, we can see here that you have -1 here, and the slope is 3, 1, 2, 3 over 1. So just looking at the equation, or if we look at the ordered pairs, let's see if these are the graph that actually, if these are the points that are actually in the graph. Okay, we have -1 and 4. -1 and 4 is here. 0 and 1, 3 and 8, so 3 and we can move up to 8, okay, and so on. So just by looking at this and also examining the slope for this line, this E represents, or this graph represents the same function as A, B, and C. And now, knowing that this is the line which has a positive slope, we can actually eliminate letter D. So of these 5 representations, A, B, C, and E represent the same function. Okay. So this concludes our session for today, and I hope to see you next week.